Hello everyone. In today's lecture, we are going to learn about the inferences for two population proportions. Previously, we learned inferences for one population proportion and one population mean. Here we talk about two population parameters, whether it be population proportions or population means. The next sections are going to talk about population means, but this particular section deals with population proportions. Now, whenever we deal with two population parameters, we are not as much focused on the actual values of the proportions or the means. Instead, we are more focused on how they compare with each other. In other words, whether both the proportions would be the same, would be almost equal to each other, there's not much difference between the portions, or whether one is less than the other or whether it's greater than the other. So that's what we are studying here. We are comparing two parameters, and whenever we compare, the operation that comes into play is difference. All right, so you will see that we will be subtracting the two population proportions, and then if we are working with mean, it would be the two means whose difference we are finding. So throughout this chapter, whenever we work with two population proportions, we should always remember that we are dealing with the difference of two values. Now, let's say we are comparing two numbers. If the difference of two numbers is 0, what does that tell us? It tells us that the two values must be equal, correct? So let's say we work with the number 5. To get a difference of 0, the other number must be the same as the number that we are subtracting 4. So when we have a difference between two numbers of 0, that means there's no difference between the two numbers, right? That means that the numbers are the same. If we were to have a negative value as a difference, correct? Let's say our difference is -1. What does that tell us about the numbers that we are subtracting? That means the second number in the difference is greater than the first number, correct? If the difference is a positive number, that means the first number is greater than the second number. So we have to keep this in mind, because that will tell us which proportion is greater than which one. Or if the difference is a 0, then we will know that the numbers are the same. All right, so just keep that in mind, because throughout this chapter we are going to talk about two populations. We will be comparing them, and we will be comparing them by taking the difference of the two values. All right? So once again, in studies of two population proportions, we compare the two proportions from two different populations drawn from independent samples. What we mean by independent samples is that the samples are not related in any way with each other. One sample has nothing to do with the other sample. So in studies of two population, there will always be two separate populations. All right, there'll be a population 1 and there will be a population 2. And from each of these populations, we will draw samples. So there will be sample 1 drawn from population 1, and there'll be sample 2 drawn from population 2. And with each of these samples, we will perform descriptive studies. We will come up with a p hat sub 1, a sample proportion from sample 1. Since this is a study on proportion, from sample 2, we will come up with p hat sub 2. And once we have those descriptive measures, we will be comparing them. Now, studies of proportion look to see whether a specified attribute has been met or not met. So even though we have two separate populations not connected in any way, we are still looking for the same specified attribute. All right. So when we send out our surveys to the members of these populations, the questions should address the same specified attribute. All right. Now here we are going to quickly go over the notations that we are going to use in studies of two population proportions. Because we are dealing with two populations, it's important that the variables are aligned to the populations they belong to. So all we do is indicate with an index value of 1 if we are referring to population 1. For variables belonging to population 2, we will just use the subscript of 2. So for population proportion, recall the notation was a lowercase p without a hat. So we will just indicate p sub 1 as the population proportion for population 1, p sub 2 for population 2. Likewise, the sample size is going to be indicated with n sub 1 and n sub 2 for each of these populations. Number of successes. What's number of successes? The number of responses that said yes to the specified attribute. That is indicated with the variable x. So x sub 1 if it pertains to sample 1, population 1, and x sub 2 for population 2, and then sample proportion with as p hat sub 1 and p hat sub 2. Now when we are computing the value of p hat sub 1 and p hat sub 2, just make sure that you are using the x value for population 1 and the n sub value for population 1. All right, the sample size from population 1. It shouldn't be x sub 2 divided by n1 or x sub 1 divided by n sub 2. Be very careful about that, because otherwise you will get the wrong metrics. All right, so this was just quickly going over the notations, and we will be using that when we are working through the problems on population proportions. Now, before we go into any inferential study, we must first consider the sampling distribution of the sample proportion or sample mean, if that's what we are working with, because that tells us what distribution we will be using, and also it kind of determines the formula that we are going to use for performing the inferential studies. All right. So it says here for independent samples of sizes n sub 1 and n sub 2 from the two populations. Now look at this over here. We talk about the mean, we talk about the standard deviation, and then we also talk about the nature of the distribution, right? But over here it's mu sub p hat sub 1 minus p hat sub 2. Again, recall, whenever we are working with two population parameters, we are always referring to the difference. So that is why they have p hat sub 1 minus p hat sub 2. So it is the mean of the difference of all possible sample proportions from the two populations, or from the two samples in this case, right? Mu sub p hat sub 1 minus p hat sub 2 is the mean of the difference, and that will always be equal to whatever the difference of the population proportion is. All right. So again, the mean of the difference of all possible sample proportions will be equal to the difference between the two population proportion. That is, the difference between sample proportions is an unbiased estimator of the difference between population proportions. And then we have for the standard deviation sigma of p hat sub 1 minus p hat sub 2. Again, the difference between the two sample proportions, and that will be equal to this formula, which is p sub 1 times 1 minus p sub 1 divided by n sub 1 plus p sub 2 times 1 minus p sub 2 divided by n sub 2, and the square root runs over the entire expression. All right. So recall that the formula for one population proportion for the standard deviation was like this. It was P times 1 minus P divided by N, right? And it was only one proportion. Over here we have two proportions, and that's why we have two of these expressions, and we have to add them up. And finally, about the nature of the distribution, P hat sub 1 minus P hat sub 2, again, that's the difference between the two proportions, is approximately normally distributed for large sample sizes of N1 and N2. So with this sampling distribution information, we are going to go into performing a hypothesis test and then finding confidence intervals. Now, previously, when we were working with one population proportion, we said that proportion studies always use the Z distribution. So here too, we are going to use the Z distribution, even though it's a study of two proportions. However, we already looked at what the sampling distribution is, what the formula for the standard deviation is for the sampling distribution. However, since in studies of proportion, we cannot use the population proportion because we wouldn't know that. We cannot use that as a test statistic because it is unknown. We have to estimate the population proportion by using the sample proportion. And what we do is we estimate the population proportion by pooling the sample proportions. So we combine the sample proportions from population 1 and population 2 using this formula x sub 1 plus x sub 2 divided by n sub 1 plus n sub 2. And whatever this proportion comes to, and that's indicated by the subscript of P, that indicates pooled sample proportion, and then we use that value in the formula for the standard deviation in the denominator of the Z calculation. So on top over here in the numerator, we have P hat sub 1 minus P hat sub 2 divided by square root over P hat sub P, which is the pooled sample proportion, times 1 minus P hat sub P, and then square root over 1 divided by n sub 1 plus 1 divided by n sub 2. So this is the formula we are going to use to calculate our Z values in the inferential studies. Now let's run through the procedure for performing a hypothesis test for two proportions. Now, at the high level, the steps are all the same as with any hypothesis test. However, what is going to differ is the way we state the hypothesis, the distribution we use, the formula that we use to find the test statistic will be specific to the study of two proportions. All right. So here we have the assumptions. We should always make sure that all the assumptions are met. The first one is simple random sample, which ensures that the study is unbiased. Then the samples have to be independent. So as I said, the samples should not be related to each other in any way. The population and the samples that are obtained from the populations have to be independent. They should not have any relation, any bearing with each other. And then the third one is that x sub 1 and n sub 1 minus x sub 1, then x sub 2 and n sub 2 minus x sub 2, all these four quantities must be greater or equal to 5. All right. First step is to state your hypothesis. The null hypothesis, which is the status quo hypothesis, will always state that there's no difference between the populations proportions. They are equal. So for the null hypothesis, use the equal sign. And it should be P sub 1 equal to P sub 2. P sub 2 will not have a value. It has to be left in variable form. Like I said, we are not interested in knowing what each of these values specifically are, but how they compare with each other. Are they equal to each other or greater than each other or less than each other, or not equal to each other. That's what matters in studies of two proportion. So P sub 1 equal P sub 2. Another alert here is please do not write P hat sub 1 and P hat sub 2. Hypothesis should always be stated in terms of population parameters. It should be P sub 1 equals P sub 2. Another mistake I commonly see is students writing mu sub 1 equals mu sub 2. There's no mean in proportions, so it should be P sub 1 equals P sub 2. The alternative hypothesis will be stated in one of three ways. Again, for two-tailed test, it'll be P1 not equal to P2, or if it's a left-tailed test, it should be P sub 1 less than P sub 2. That means the population proportion 1 is less than population proportion 2, and if it's greater than, then it's a right-tailed test. In step 2, we decide on the significance level alpha. Significance level will be given to you in the question. It will tell you at what significance level you have to perform the test. Make sure that you convert it to a decimal value and use it for alpha. All right. They've given us the formula here. Z equals P hat sub 1 minus P hat sub 2 divided by, this is the standard deviation formula for the pooled proportion. You see over here we have P hat sub P. So we have to use the formula, a very easy formula to find the pooled proportion, which is just add x sub 1 and x sub 2 and divide it by n sub 1 plus n sub 2. Right? So these are the first three steps, and then we go into the critical value approach, the p-value approach, take a decision, and then finally make an interpretation of our test. So here are the remaining three steps. Studies on proportions use the z distribution, so our critical values are going to be z values, which you can obtain from your table, or if you have a graphing calculator, you can use that too to find the z value of the z distribution. And in critical value approach, we demarcate our standard normal curve with reject regions and do not reject regions, correct? So if it's a left tail test, reject region will be to the left. If it's a right tail test, reject region will be to the right. If it is a two tail test, reject regions will be on both ends of the curve. However, to find the critical values, which is the z of alpha by 2, for two tail test, it's going to be a negative value and a positive value, but you have to divide your alpha by 2. You have to split your alpha value just for two-tailed test. For left-tailed and right-tailed test, you do not need to split your alpha value. It only applies to two-tailed tests. And once we define the regions on our curve, find the critical value, we bring our test statistic from step 3. If the test statistics falls in the rejection region, we have to place the test statistic value against our diagram. If it falls in the rejection region, we will reject the null hypothesis. Otherwise, we do not reject the null hypothesis based on the criteria we came up with. For p-value approach, we start with the test statistic value, indicate that on our diagram, on our standard normal curve where it is likely to be located, and then we find the corresponding area. If it's a left-tail test, it's the area to the left of that test statistic, wherever that is located on the curve. If it's a right-tail test, then your z value will be to the right of the 0, the center point, so it'll be the area to the right. That would be the probability of obtaining that particular test statistic. And if it's a two-tail test, you can find the area on any one side, but you have to make sure that you double it, you multiply it by 2, and then compare it with alpha. And what is the logic we use in the p-value approach? If p is less or equal to alpha, we compare p with alpha. If it is less or equal to alpha, we can reject the null hypothesis. Otherwise, we do not reject the null hypothesis. And finally, we interpret the results of the hypothesis test in context of the problem that we are trying to test out. All right. Now here we are going to work through an example and apply the procedure that we just learned about for performing hypothesis tests for two population proportion. Now this particular example is about eating out vegetarian. I'm going to read through the question and we have to try to understand what the study is about, and we have to determine where the two population or what the two populations are and what data apply to each of those populations, right? So it says here, Zogby International surveyed 1,181 US adults to gauge the demand for vegetarian meals in restaurants. The study polled independent random samples of 747 men and 434 women. Of those sampled, 276 men and 195 women said they sometimes order a vegetarian dish when they eat out. We want to use the data to decide whether the percentage of men ordering vegetarian is smaller than that of women. So here, what is the study about? The study is to determine the demand for vegetarian meals in restaurants, correct? And not just vegetarian meals ordered by the general population, but there are two populations. They want to know the proportion of men ordering vegetarian meals versus women ordering vegetarian meals. So as it says here, they want to determine if the proportion of men ordering vegetarian is smaller than that of women. So here we are comparing. We have to find the proportion of men ordering vegetarian meals and then women ordering vegetarian meals, and then compare them and check if men order fewer times than women. All right. So first is to formulate the problem as a hypothesis test. This particular question says, what is the specified attribute they are looking for? Recall that proportions are about checking for a specified attribute. So in the questionnaire that was sent out, the question was probably, do you order a vegetarian dish when eating out, right? So that is the specified attribute, and those who responded would either respond as, yes, I order vegetarian dish sometimes, or I do not order vegetarian dish. So whoever said yes met the specified attribute. So in this case, the specified attribute we are looking for is ordering vegetarian dish when eating out. What are the two populations that we are concerned with here? Population 1, and it's up to us to determine which is population 1, which is population 2. But we'll just say population 1 is all US men, and then population 2 is all US women. All right, so these are the populations. And recall that populations would be all. It would mean the entire population. Sample is a portion of the population, but whenever we refer to the population, it's all US men. It's not 747 men. That's the sample size for men. But whenever we refer to the population, it better be all US men and all US women. Now, the next set of questions for the same study asks us to denote and state the population proportions. Previously, we were asked to just identify the two populations, which was all US men and all US women. Here, they're asking us to denote and state the population proportions. So the way we state that is P sub 1 without the hat. Recall they are asking for population proportion. So no hats over the P. It's going to be P sub 1 equals proportion of all US men who sometimes order vegetarian, and P sub 2 equals proportion of all US women who sometimes order vegetarian. And then we come to stating the null and alternate hypothesis. Null hypothesis always uses the equals. It's P sub 1 equal to P sub 2. P please make sure you're using the population proportion notation. There shouldn't be any hats over the P when stating the hypothesis. So P sub 1 equals P sub 2, which means the percentage of men is not less than that of women ordering vegetarian dishes. Correct? It's the same as what the null hypothesis is stating. Alternate hypothesis is stating P sub 1 is less than P sub 2. How did they come up with less than P sub 2? Go back to the question. It should state in the question what they want you to test. It says here, we want to use the data to decide whether the percentage of men ordering vegetarian is smaller than that of women, and that is the reason they have used the less than sign in the alternate hypothesis. So what tailed test is it going to be? It's going to be a left-tailed test, correct? Now we are going to work through the entire hypothesis test, starting with extracting the data from the verbiage of the question that we have up here, right? It's the same problem, eating out vegetarian, but we need to first obtain the different values that we will be using for our calculations. Now, I always say this, and I will say it again, that the best thing to do is have the formula in front of you, because that will help you determine what data you need for your calculation. So I'm going to quickly write down the formula up here, and then it'll help us obtain the necessary data for our testing. So here's our formula. Z sub 0 equals P hat sub 1 minus P hat sub 2 divided by square root over P hat sub P, which is the pooled sample proportion, times 1 minus P hat sub P times 1 divided by N sub 1 plus 1 divided by N sub 2, with the square root running all over that expression. All right. So P hat has a formula of its own. So I'm just writing the formula for P hat. It's x divided by n. So if it's P hat sub 1, then it'll be x sub 1 divided by n sub 1. We need to know what n is. We need to know what x is. And then to calculate P hat sub 1, we will of course need to know what n sub 1 is, n sub 2 is, x sub 1 is, x sub 2 is, right? So what is n? N without a subscript means the entire sample, men and women put together, and that's 1,181. So let's write that here. It's going to be 1,181. N sub 1. Now, population 1 and sample 1 refer to men. All US men represent population 1. So N sub 1, the sample size for men, is 747. Let's write that down here. 747. N sub 2 is the sample size for women, so 434. Now X sub 1 is the number of men that responded with a yes. What is that value? Of those sampled, 276 men said they order a vegetarian dish. So that's going to be X sub 1, 276. X sub 2 is the number of women that responded saying they order a vegetarian dish. So that's 195. So P hat sub 1 is going to be x sub 1 divided by n sub 1. All right, be very careful there. We have to make sure that we use the right values to find our sample proportions. And I already see a mistake here, which I'm going to correct, that this one is going to be P hat sub 2. So P hat sub 1 will be 276 divided by 747. And that should give us a proportion of 0.369. Let me use the blue color here. It should give us 0.369. That's the P hat sub 1. And P hat sub 2 will be for women, so 195 over 434, which is 0.449. So these are our P hat sub 1 and p hat sub 2 proportions. Check assumptions. What are the assumptions? Simple random sample. They should be independent. So let me write that. It should be SRS, and the question itself says they were random samples, then they need to be independent. So both those conditions are met. Independent samples. Where does it say? Over here it says independent samples. And the other one is that X sub 1 comma N sub 1 minus X sub 1, then X sub 2 comma N sub 2 minus X sub 2 equals, well, not equals, but greater or equal to 5. That's a necessary condition. And if you do the subtraction over here, X sub 1 is 276. Therefore, N sub 1 minus X sub 1 would be greater than 5. Same with X sub 2 and N sub 2 minus X sub 2 as well. So all four quantities will be greater or equal to 5. So all assumptions are met. We can proceed with our test. State null and alternative hypothesis. We already did that previously, but let's do it again anyway. H sub 0, the null hypothesis is going to state P sub 1 is equal to P sub 2. And the alternate hypothesis is going to state that P sub 1 is less than P sub 2. Correct? Less than, because the question says we have to test whether the proportion of men ordering is less than the proportion of women. Decide on the significance level. It doesn't say here, so we'll just make it a 5% significance level. We'll test at the 5% level. You have to convert the 5% to an alpha value, a decimal value. So alpha is going to be 0.05. So here we are going to calculate our test statistic, which is going to be a z value using this formula given here. Now, I've already written out some of the quantities that we calculated previously for p hat sub 1, p hat sub 2, and then we also have to calculate p hat sub p using this formula. And I've done the calculation here, and I came up with this proportion 0.399 as the pooled proportion, which we are going to have to use in the denominator of the equation. So just make sure you are plugging in the values correctly in the formula, and also that you are applying the formula correctly. So p hat sub 1 is 0.369, it's this value here, minus p hat sub 2 is 0.449, which is the numerator, and then let's go to the denominator. P hat sub p is 0.399, so 0.399. All right, now I'm going to just follow the formula as is, but you can just use a single square root as well. All right, so 0.399 times 1 minus 0.399. So for the denominator, you're not using p hat sub 1 or p hat sub 2. You are using the pooled proportion. So make sure you do that calculation using the formula given. And then we are still not done with denominator. There's another square root. So 1 divided by n sub 1 is 747. That's the sample size for men, plus 1 divided by 434, which is the sample size for women. And once we complete this calculation, and it's always good to indicate the test statistic with a subscript of 0. So you should come up with this value, negative 2.726. And that's the test statistic that we came up with using the data given. Now we will take over the test statistic to the two approaches, critical value and the p-value, and complete the test. So at this point, we are going to start with the critical value approach. All we need from here on is what the test statistic value is. Z sub 0, the value we found was negative 2.726. All right, negative 2.726. Now we start the critical value approach by first drawing a standard normal curve. So I'm going to draw that here. I'm going to sketch it. So here's our curve, the standard normal curve, and we have to show reject and do not reject regions. This was a left tail test because we are trying to test whether the number of men or the proportion of men ordering vegetarian is less than the proportion of women, correct? So that made it a left tail test. So the reject region is going to be on the left hand side, right? And the do not reject region is going to be on the right hand side, on the other side of the reject, in other words. And this area which falls under the reject region is going to be your alpha value, correct? It's this, just a second, this is going to be 0.05, and that's the alpha value obtained from the significance level percentage that we were asked to test at. We have to find this Z value corresponding to 0.05 alpha value. Again, because this is a left tail test, our Z value is going to be negative Z of 0.05. So we have to take our alpha value and we have to look up our table to come up with the corresponding Z value. So the critical value is going to be negative of Z of 0.05, and if you look up the table you should come up with a value of 1.645, and remember it must be a negative value. So let me put that here. It has to be a negative 1.645, and I'm going to write that here as well, negative 1.645. And now that we have defined our criteria using the normal curve, we showed our reject region, do not reject region, we came up with a cutoff between the reject and do not reject region, which is the critical value. Now we can bring our test statistic value of negative 2.726 and see where that falls in our diagram here. So negative 2.726 is a way smaller value than negative 1.645, so it's going to fall way to the left of the cutoff point. It's going to fall in the reject region. So it's going to be way to the left, somewhere here maybe. Just mark it somewhere to the left in the reject region, negative 2.726. So let's come to a conclusion based on this. So Z sub 0 of negative 2.726 is less than negative 1.645. All right, it falls in the reject region. Please make sure when you're working these questions on assignments and exams, you also write down the conclusion that you came up with from the critical value approach and how you came up with that conclusion, right? It falls in the reject region, therefore reject the null hypothesis. Reject the null hypothesis. Recall that the null hypothesis stated that there was no difference between the proportion of men and women ordering vegetarian. So when we reject the null hypothesis, that means that's telling us that the proportion of men ordering vegetarian is indeed less than the proportion of women ordering vegetarian. All right. So now let's go to the next slide where we will be using the p-value approach to come to a decision. We should get the same reject decision, but let's do it using the p-value approach. Now for the p-value approach, we first start with the test statistic and represent it on the standard normal curve. So here is my standard normal curve, and we have to show where that test statistic value falls on the standard normal curve. So our test statistic value was negative 2.726, correct? It will be somewhere to the extreme left, maybe here, negative 2.726. Now there are no reject and do not reject regions with the p-value approach. All you do is on your diagram show where your test statistic would lie, and then because this is a left tail test, you're going to find the area to the left of negative 2.726, and that is going to represent the p-value. So I'm going to just indicate it here. The p-value is this area. So we have to find that area. That's going to be the p-value corresponding to the test statistic value of negative 2.726. It's the area to the left. So I'm going to use my calculator. The p-value is going to be, so let me write down the step. Find area to the left of z sub 0 of negative 2.726, and that's going to be a very small value. It's going to be something like 0.00321, I don't know, 1 probably. All right, so it's a very small value, and the next step you compare. This is our p-value. Let me write that here. This is p-value. So compare p with alpha, correct? And if p is less or equal to alpha, then the decision is to reject. So our p-value was 0.00321. Is it less than 0.05? Of course, yes, correct? Yes. Is it less than 0.05? Yes. Therefore, the decision is to reject the null hypothesis. Now, I obtained this exact p-value using my calculator. However, if you have to rely on your table, you can still find the exact p-value if it is a z distribution. For t distributions or any other distributions, you will have to estimate because they all depend on df's, degrees of freedom, and we never get a complete table on paper, right? But for the z test, for the z distribution, we have a complete table. So I'm going to pull that up and show you how we can find the p-value from the table. So here I have the table. We are going to go to our z column and find negative 2.7. The first decimal place is 0.7, so negative 2.7. So this is the row that we are going to focus on. We have only 2 decimals represented on the table, so I'm going to round this negative 2.72 to negative 2.73. So now we go across to 0.03, and you see over here the value that intersects with negative 2.7 from the row and 0.03 from the column is 0.0032, and that is what we got here. All right, so this is how you're going to use the table to find the p-value. You will get the exact p-value if you are using the z distribution. All right. Now we are going to formally state the decision that we arrived at and write an interpretation of the results. We've already explained the reasoning behind the decision when we work through the 2 approaches. Here we can just state that the decision was to reject the null hypothesis. And finally, for the interpretation, you always have to start with the significance level at which you were testing. So at the 5% significance level, the data provides sufficient evidence. When we are rejecting the null hypothesis, then your data was strong enough to reject the null hypothesis. So you have to write it accordingly. The data provides sufficient evidence to conclude. And for the rest of the interpretation, you can just take the verbiage from the question itself. So the data provides sufficient evidence to conclude the percentage. So just copy everything from here. The wording, the percentage of men ordering vegetarian is smaller than that of women. Right? So just copy that to conclude that. The percentage. So here you go. At the 5% significance level, the data provides sufficient evidence to conclude that the percentage of men, actually we should be writing of all US men ordering vegetarian, is smaller than that of women, right? Now there's one more inferential study we need to complete for two proportions, and that is to find the confidence interval. The confidence interval is going to be an interval of differences between the two proportions. The general steps of finding a confidence interval is the same as any other study. However, the formula is going to change, and also the distribution that we use will also change. All right, so let's go through the process here. First of all, the assumptions are the same as the ones for hypothesis test. It has to be simple random sample. Then the samples need to be independent, unrelated to each other, and x sub 1, n sub 1 minus x sub 1, x sub 2, and n sub 2 minus x sub 2 must all be greater or equal to 5. In step 1, since we are using the z distribution, we will be using our table to find z of alpha by 2. So whatever percentage confidence interval you are using, you have to convert that to alpha by dividing that percentage by 100, and then you have to divide that alpha value by 2. Correct? That is for any confidence interval. And then to find the endpoints of the confidence interval for P1 minus P2, again, this represents a difference between the two proportions. This is the formula that we will be using. So we have to subtract the two proportions, which will be our point estimate, and then plus minus the z of alpha by 2 value, and then the standard deviation formula. But this time we are not using any pooled proportion. We are using the individual sample proportions we found from our sample study. And then finally we interpret the confidence interval in context of the problem. So let's finish off this lecture by finding a 90% confidence interval for the difference of the two proportions for the same problem on figuring out the demand for vegetarian meals in restaurants. It's the same problem for which we performed a hypothesis test, right? Again, this is going to be an interval of difference between the two proportions. So the point estimate is not going to be the proportions themselves, but the difference between the two proportions. The first step is to check the assumptions. Now I'm going to skip that because we already checked the assumptions when we were performing the hypothesis test, and the assumptions are the same. So I will just skip this in the interest of time, and I'll just say yes, all the assumptions were met. The next step is find z of alpha by 2 using the z table. But in order to find z of alpha by 2, we need to know what alpha is. Alpha will be determined from the percentage confidence interval that we are finding, correct? So if the confidence interval is a 90% confidence interval, then the confidence level is the decimal version of the 90%, which is 0.90. So alpha is 1 minus 0.90, which is 0.10. But you have to divide alpha into two equal parts. For any confidence interval calculation, alpha will need to be divided by 2, and that will be a 0.05. So now we will have to find z of 0.05, which has a z value of 1.645. All right. So now that we know our z value, we will need to find the endpoints of our confidence interval. Like, as I say, always have the formula before you because it'll help you to plug in the values correctly and also determine what variables are there in it, what values you need to plug into the formula. So I'm just going to pull up the formula here. So here is the formula to find the endpoints of the interval. So over here you see the point estimate right here. This is the point estimate. It's a difference of the two proportions we calculated previously, and I'm going to write those two values. So let me do that here. P hat sub 1 was 0.369 and P hat sub 2 was 0.449. And we know the value of z of alpha by 2, which we just found in the previous step. It was 1.645. So let's go ahead and plug in the values here. Always surround the point estimate because it's the difference of two values. It's just good practice to surround it within brackets. So P at sub 1 is 0.369 minus 0.449 plus minus, and then z of alpha by 2 is this value here, 1.645 times square root over P hat is 0.369 times 1 minus 0.369 divided by n sub 1 is 747 plus again P hat sub 2 is 0.449 times 1 minus 0.449 divided n sub 2 is the sample size for women, which is 434, correct? So once you complete the calculation, well, let's find what the value of the margin of error is. So margin of error is what we add and subtract from the point estimate, correct? So P hat sub 1 minus P hat sub 2, which is the difference of these two proportion values, is going to be negative 0.080. And this calculation of the margin of error comes to 0.049. And when you do the addition and subtraction, we come up with the two endpoints to be negative 0.129 to negative 0.031. So this is the confidence interval. It stretches from negative 0.129 to negative 0.031. Now, one thing I want to talk about here is how to analyze the confidence interval values. How do we interpret the confidence interval after we come up with the endpoints, in other words? Now, remember that these values are differences. These are not proportion values. Proportions cannot be negative, right? So these are difference between the two proportions. Now, when both the endpoints have the same sign, whether it be minus or plus. So if the lower end is a minus and the upper end is also a minus, or if the lower end is a plus and the upper end is also a plus, that means there is significant difference between the two proportions, right? That should be the conclusion. So same sign on both ends, whether it's minus minus or plus plus, indicates that there's a difference, a significant difference between two proportions, all right? Difference exists. However, if one of the endpoints is a negative, so if the lower end is a negative and the upper end is a positive, that means no difference exists. They are almost the same. And think about it, when we have a negative, let's say here is our interval of values. If one end is a negative and the other end is a positive, I'm just writing some values here, then this interval contains a 0 in it. It contains a difference of 0 within that interval. And because this interval is one of differences, when the difference is a 0, what does that tell us? When the difference of two numbers is a 0, that means the numbers are the same. And that is why if the endpoints of the confidence interval are two different signs, one negative, the other positive, then the conclusion should be that there's no difference between the two proportions. And that should agree with your hypothesis testing decision as well. If your hypothesis testing decision was reject, then your confidence interval should either have both negative signs or both positive signs in its endpoints. If the hypothesis test decision was do not reject, then most certainly your confidence interval will have one negative and one positive on the upper end. So when we study two proportions or two means, the same logic will apply when we go into studying the differences of means as well. All right?